In this problem, we're going to consider a situation where there is two springs coupled together. They each have the same length, but they have different spring constants. This has, say, a spring constant of K1, and that's K2, and they're suspended by two structures that are a distance of 2L apart. Then imagine that we attach a mass right here and then pull it down until each spring is stretched until its total length is not L, but 2 times L. So it'll look something like this. Each spring has 2L, spring constant of K1, and this has a spring constant of K2. Then after we pull the mass down, we release it. We want to know, once we release it, what will be the acceleration on that mass. And it looks like there's going to be not just several forces acting on it, but these forces will have vertical and horizontal components. Of course, we have the weight pulling it straight down. And then this spring will have a restoring force in this direction, and this will have a restoring force in this direction, but it looks like that can probably be resolved into a vertical and a horizontal component for each one. So let's see if we can dissect this and figure out what these different force components are. Now, this is 90 degrees for this triangle, and this side is length L, its hypotenuse is 2L, so the angle here, the sine of that angle will be the side opposite of it, divided by the hypotenuse. That's 2L, or L divided by 2L, so the sine of this angle is 1/2, so this angle should be 30 degrees, and likewise for this angle, because the sine of this angle will be the side opposite from it, L, again divided by 2L, to give 1/2. So we know that much about it. Let's consider what the vertical forces would be, and the vertical forces we'll consider acting in the y direction. So we have the mass M, and of course gravity, that's a vertical force that goes straight down. And then the spring, this one, it exerts a force in this direction. The magnitude of that force will be the displacement of that spring, and that's L, because it was L and it got stretched out to 2L. So this was stretched a distance of L, and the force that it exerts will be the spring constant times that displacement. So let's represent that like this. This is L K1, and likewise this spring was stretched a distance of L, so the force that it exerts in this direction would be L times K2. So there we have it right here. And then we have this vertical line like this. And this angle is 30 degrees. So let's imagine this triangle here, where we have this, 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 and here this would be the hypotenuse of it. It points in this direction. It has a magnitude of LK1. This angle is 30 degrees. So the force in this direction right here Now this is adjacent to the angle. This side here is opposite from the angle. This side is adjacent to it. So the length of this side, which would be the force going straight up, that would be equal to LK1 times the cosine of 30 degrees. So we could say that Fy1, one of the forces acting upward, that is LK1 multiplied by the cosine of 30 degrees. And over here, it looks like this is going to be a similar deal, because this angle here is also 30 degrees. So let's consider this triangle where we have the vertical. Here's the hypotenuse. The hypotenuse is pointing up in this direction. It has a magnitude of LK2. And again, this is 30 degrees. And we want to know what will be this force. And clearly that will be going up like this. And that will be equal to the magnitude of the hypotenuse, again, times the cosine of 30 degrees. So you have LK2 times cosine of 30 degrees. And again, it's the cosine because this is the side opposite of 30 degrees. This side, the one that we're interested in, is adjacent to that angle. So this would be the hypotenuse times the cosine of 30 degrees. So we have Fy2. The second force acting straight up has this magnitude. So we have Fy1 is this, and Fy2 is this, so the total force in the y direction resulting from the springs would be this plus this. So we have LK1 plus LK2 times the cosine of 30 degrees. LK1 plus LK2. And the cosine of 30 degrees, that's the square root of 3 over 2. So this force here, resulting from both of the springs pulling upward, that has this magnitude right here. So the net force, the net upward force acting on the block, that is this minus this. So we have F of y minus mg. That's the net force acting on the block, so that would be equal to the mass of the block times its acceleration, its vertical acceleration, ay. Y, of course, is designating the vertical direction for our problem. So we have the acceleration in the y direction will equal this divided by m. So we have f of y over m minus g. That is then the acceleration in the y direction. So it looks like we're going to have that a y is equal to this divided by m minus g. So with this, we can factor out the L here, and we have a square root of 3, so we've got the square root of 3 times k1 plus k2 divided by 2. We have to divide it by m. We have this L. Then subtract g. So that is our equation then for the vertical acceleration that is acting on the object. Now, that's not the only force to consider, though. So we go back to here where we have these forces exerted on the objects by the spring, they have a vertical component. We just figured out what they were, but clearly they can also have a horizontal component as well. So we now have to figure out what are the horizontal components. So let's try to redraw all of this and see if we can figure out what the horizontal forces are acting upon our object M. Remember, now here is our equation then for the vertical acceleration. And once again, let's try to redraw this part of the diagram. We have the mass M, and then there's a force like this from this spring, and the magnitude of that force was Lk1. Then there's the force from this spring, that's Lk2, and now we want to consider their horizontal components. Now, this angle is 30 degrees, so this angle is 60 degrees. Of course, over here it is 60 degrees. So let's draw this a little bit neater. We have Lk1 like this. Then we can just go straight down, and its horizontal component is this. So this is Lk1. It's the hypotenuse of this triangle. That angle is 60 degrees right here, and we want to know that side of the triangle. So that's going to equal Lk1. Here's the angle. Now this side is opposite of it. This side that we're interested in is adjacent to it. So this is going to be equal to Lk1 times the cosine of 60 degrees. And that will be, we can call this Fx1. And that's the force, the horizontal force in this direction, Fx1. And that's the magnitude of it. Now over here on this side, we're going to have, again, a similar deal. Here we have this hypotenuse, Lk2. We want to know this component. This is a right angle, so that's the hypotenuse. And again, that angle is 60 degrees. So this side is going to be Lk2 times the cosine of 60 degrees. So Fx2 equals Lk2 times the cosine of 60 degrees. And this is pointing like this, so its horizontal component points in that direction. So here, the force pointing in this direction, Fx2, we know what that is. That's this. So the net force acting in the x direction would be this minus this. So the net force in the x direction, call that f of x, equals Fx2, say, minus Fx1. Fx2 is this, Fx1 is this, so that equals Lk2 minus Lk1 times the cosine of 60 degrees, and the the sine of 30 degrees is the square root of 3 over 2, so the cosine of 60 degrees is 1/2. So that's the force in the x direction, and of course that will equal the mass of the block times its acceleration in the x direction. So we have the acceleration in the x direction equals f of x divided by m. So we divide over here by m. And we have ax that equals k2 minus k1 divided by 2m times L. So there's the acceleration in the x direction. And of course, a few moments ago we determined what it was, the vertical force, or the vertical acceleration, ay. So the total acceleration, of course, will be ax squared plus ay squared. And we know what each of these are, so if you want to, we can determine what the net acceleration is. Okay, that's all we had to say for this video. The playlist for the analytical mechanical series, or analytical mechanics, that playlist is found at the website digital-university.org.